Hello.
Hey, Andrew.
How's it going?
Are you fully moved to Boston now, Andrew?
I'm in Boston. All our stuff is here. Lots of boxes around, but depending on how you define fully moved, yes.
Yeah.
I didn't realize you were coming to Boston.
Yep, I'm starting at MIT.
Oh, nice. Congrats.
Thanks.
All right, it's now 9 a.m. East Coast time at least, so let's begin. Good morning or good afternoon or good night, everyone. I'm Megan Bedell. I am an associate research scientist at the Center for Computational Astrophysics at the Flatiron Institute. And I'm very happy to be moderating the data analysis panel to kick us off on this Thursday. So we have some excellent panelists and some excellent data to talk about here. We've been hearing a lot of great astrophysical applications of TESS data for the past few days, and it's clearly having a big impact on the field. So it will be great to spend some time talking in more detail about the analysis that underpins all of these results. So I'm going to introduce our panelists one by one as they give their short summaries of the longer talks that are available on the YouTube channel. And we're going to go in rough order of analysis steps from TESS camera readout to final results, mainly focused on exoplanet discovery for this panel. And starting us off will be Adina Feinstein. Adina is a grad student and NSF fellow at the University of Chicago, and she is the lead developer of some great TESS analysis codes, including the Eleanor package for extracting light curves from FFIs, which is what she's going to be telling us about now.
Morning, everyone. Thanks so much for tuning in this early, this late, or this middle of the day. I'm sure that joke definitely won't get old as we're on the 4th day of the TESS conference. And thanks to the organizers for inviting me to give this talk. I had a lot of fun learning about, I already knew about all the other great codes that are out there and other light curves, packages and whatnot. And so I had a great time, going over all of those in my overview talk. So can you see my slides okay right now? Sweet. Yeah, so I will give a short summary of everything that I've covered, but definitely go check it out if you want to learn more about all of the packages. So I know Megan just said that this panel will be focused more on exoplanet science, but I really just wanted to highlight all of the cool science that can be done in the flow from images that definitely wouldn't have been accomplished otherwise. And so going from, finding new exoplanets from all the way on the left here to talking about astroseismic modes, stellar flares, stellar interior structures in the middle, even moving out to extragalactic, which we heard about on the first day. So talking about supernova, and then tomorrow, I think we'll be finishing up talking about solar system science. And so I've pulled a little GIF here of series that I made using Clara Browser's tool, TESS Cut, which is available on MAST, which is a very, very, very sweet tool. So I basically covered the 3 methods that most teams have used to extract light curves from the TESS flow from images. The most popular one being aperture photometry, where you apply a mask to your pixels and then sum them up over time. Also talking about difference imaging, which is the second most popular method that had been used, where you're subtracting images, which is a great way to actually remove some of the large background systematics that we've seen in TESS, and I gave some examples of that as well. And then lastly, talking about point spread function modeling. So looking at how your pixels respond to the detectors and then trying to model that as accurately as you can, which is a little bit hard with TESS because the pixel response function changes as a function of where you are on your CCD, but it can be done. And it also can be estimated fairly well using simple models. So just as an overview, I guess here are all of the teams that have provided light curves and or open source tools to extract light curves from the full frame images. And so what I went through with my talk was going through each of the methods and the science goals from these teams here. So talking about the cluster differencing imaging pipeline, CDIPS to Diamante, Eleanor, which is my own code. And although we don't provide light curves on the Mikulski Archive Space Telescope, we do provide the code for that. Light curve, which is also a great tool that uses test-cut behind the scenes now to extract light curves. The MIT Quick Look pipeline, Pathos, which we heard about yesterday. Difference imaging pipeline from Olkers and Stassen, the SPOC team, and then the TESS Asteroseismic team, which are all great. And from that, I also tried to break it down for anybody who hasn't used the full frame images before into what the science goals were for each of these teams and then what methods they used and where they can be found online. I hope that this is a kind of useful overview table for, if you're interested in looking at young stars, maybe you'll go to the CDIPS team. If you are interested in exoplanets, maybe the Quick Look pipeline. But I think the main takeaway is that you should really use all of the light curves that are available to you. And so even if you're just using one light curve right now, it's always good to cross-check your signals for other teams. And then at the end of my talk, I gave these cute little GIF animations of how you can go about extracting light curves from a Python notebook. And I also want to plug that we'll be going over more of this and comparing light curves directly this afternoon in the TESS full frame image splinter session that's being run by Sam Grunblatt. Yeah, I think that's all that I had for my overview. Thanks.
Great, thank you, Adina. So next up, we're going to hear from Rodrigo Luger. Rodrigo's a Flatiron Research Fellow at the Flatiron Institute, CCA. He's developed some really impactful code, including the STARRY package for mapping stars and planets and the Everest code for detrending K2 data. And he's going to be telling us more about detrending light curves with TESS. Take it away, Rodrigo, please.
Yeah, thanks, Megan. It's a pleasure to be here. My talk was a little long. I apologize. It's mostly pedagogical. And so here's just a really brief summary. The idea is motivating linear models as a simple but extremely powerful way of modeling noise in test data, but also more generally in any kind of time series data. Basically, you're just modeling everything as a Gaussian, as a multidimensional Gaussian. And so on this slide here, what I have is F is some observation you've made of your light curve. And we're just saying that this is distributed as a multidimensional Gaussian, as a normal distribution, with some mean substar, which stands for astrophysics, that's something you care about, plus some component you don't care about, which is the systematics, some component from the instrument or the detector, et cetera. And so it has a mean and a covariance, which you may or may not know as well, but this is typically just your error bars on your data. So given this assumption that your distribution is Gaussian and that your noise model is linear, you typically have two options. The first one is to detrend, which is what people are most used to. And that entails finding the best fitting value of these W coefficients. By the way, this is just a matrix equation. A is some matrix that characterizes the detector, and W is the coefficients that characterize that particular detector, that particular observation. And so one option is to find the best solution for W, subtract it off and get a detrended light curve, or to marginalize over the unknown systematics, to actually treat it as a nuisance parameter and take the Bayesian approach of I have a prior on what these should be, I'm going to marginalize or integrate over them. The cool thing about the detrending approach is that if you have a linear model, the light curve, the detrended light curve F prime, you can just write down the expression in closed form. It just involves some matrix inverses. And by the way, I go into a lot more detail in my actual talk. So if you're interested in this, please like sit through the longer version. The main drawback of detrending, there are two. The first one is that the detrending process correlates data points. And so just reporting an uncertainty on your detrended light curve isn't enough. You should actually report the covariance matrix. But the biggest downside is that in order to detrend, you actually see that on the right-hand side of this equation, you have the astrophysical signal that you're actually interested in. So in other words, in order to properly detrend a light curve, you have to remove the astrophysical information so that then you just have instrumental stuff so that you can fit it out. And then you put the astrophysical information back in. But that's usually the reason you're detrending is because you don't know the answer. You don't know what the actual astrophysical signal is. And so it's a bit circular. And there are ways around this, right? So one way around this is you mask the transits before you detrend so that the detrending process doesn't overfit them. For stellar variability, it might be a little bit more complicated, especially when the time scale of the instrumental variability is comparable to the time scale of the astrophysical variability, then it's not so clear what the detrended light curve is actually doing and if it's fully removed the astrophysics or not. So that's one of the drawbacks of detrending. Then very briefly, the alternative to this, if you have a linear model, is to marginalize, is to actually not compute a detrended light curve, but actually compute the joint likelihood of your astrophysics model and your systematics model simultaneously. And the cool thing about linear models is that they allow you to write down a closed form expression for this likelihood. And so you just stick this in an MC-MC chain or some kind of posterior inference scheme to actually simultaneously model your physics while marginalizing over your systematics. And I go into more detail about this in my actual talk. There are several approaches to doing this with test data. A simple way of incorporating a linear model is to use co-trending basis vectors, or PCA. This is done by many of the pipelines. PCAs, this is a linear model, right? You're finding the best fitting coefficients for each of these basis curves and subtracting them from the data. Another one is pixel level decorrelation. This is something that was developed for Spitzer initially, which I then extended to K2. And the light curve package implements this for TESS as well. This uses information at the pixel level to detrend the SAP, the simple aperture photometry data. There are a couple other tools that I mentioned in my talk too. One is linearized field deblending. This is a point spread function modeling technique that Christina Hedges developed. It is a linear model. You're building, you're learning what the PSF is from the postage, from the full frame image, essentially. And so it's great when you have blended sources. And then another one also by Christina Hedges is TESS backdrop, which is a linear model for removing large scale systematics from full frame images, from the actual background of full frame images. I think I'm at 5 minutes, so I'll just end there.
All right, well, thank you, Rodrigo. And I have to say, even if Rodrigo's YouTube talk is on the long side, I think it's very much worth watching and seeing the detail on all of these things. Let's see, next up we have Jason Eastman. Jason is a research associate and lecturer at Harvard-Smithsonian Center for Astrophysics, and he's the lead developer for ExoFast v2, which is a great piece of software for fitting star-planet systems, which has been used in a really impressive number of TESS discoveries. And he's going to be telling us about modeling exoplanetary systems. Take it away, Jason.
Sorry,
Jason, you're muted. Yeah.
Okay. Okay. Now I gotta find my screen again. Okay, there we go. Sorry about that. Thank you for that introduction. Yeah, I'm Jason Eastman. I'm from the Center for Astrophysics, Harvard and Smithsonian. My longer talk goes into a lot more detail about the transit and radial velocity modeling. But here I just want to focus on something that I think a lot of you are probably less familiar with. And so hopefully that's more useful. So here, just for a very brief introduction to the transit modeling, this is just showing the star and what we interpret this to be, and this is what you would get for a light curve of of this 3-planet system. This is actually a K2 system, GJ9827. But I want to focus for this short talk on modeling the star, because I think that's super important, and ultimately everything that we know about the planet scales with the properties of the star. Okay, so the really nice thing about, as of a few years ago, Gaia DR2 released parallaxes for just about every planet hosting star that we could ever hope to find. And so that gives us a way to model the SED, the spectral energy distribution. That's what this curve is on the right, because we can combine the Gaia broadband photometry with the broadband photometry from all sorts of different all sky surveys like WISE and 2MASS and Gaia itself, and sometimes other surveys that are readily available, along with the parallax and maybe limits on the reddening that we see. And then we can just automatically get a very good constraint on the radius and the luminosity and the volumetric flux and even the temperature and sometimes even the metallicity of the star just from the SED itself. And if you combine that with a stellar evolution model, you can actually get very, very precise results. And they're not just precise, as Jamie Taylor and Diego Godoy Rivera showed. They compared some results that they fit just with ExoFast using the SEDs and the evolutionary models, compared that with Asteroseismology, and they get very, very good agreement. So they're precise and they're accurate, which is nice. And so I think that's a really important part of modeling the planet, because you have all of the planetary parameters scale with the stellar parameters, and so you have to know the star very accurate. And so if you just compare the results that you get, if you just pull out the values for log G and effective temperature from the TIC V8 and you plot them together in an HR diagram, you get this plot here, and there's quite a bit of scatter here. But if you take all of the TOIs and you run them through ExoFast and you just do a star only fit with all publicly available information, you get a much tighter HR diagram here. And so you can tell just from publicly available information, no instruments required, nothing else required, you can improve the stellar parameters dramatically. But I want to caution you that in the age of Gaia, it's very, very easy to get statistical errors that are much smaller than the systematic errors. And so if you find yourself quoting errors that are lower than 100 degrees in effective temperature, or 0.08 dex in metallicity, or about 2% in radius, you should be worried that you're actually systematics dominated, and you're going to over or underestimate the errors in not only your star but in your planet. But the cool thing about including the star within the model is that you can now include additional effects that are often negligible in your planetary model, like the reflex motion of the star. Or you can also include eccentricity constraints where planets can't cross into each other's Hill spheres. And probably the most important one is including the light travel time. So when you observe radial velocity, you're actually seeing the information as emitted from the star. But when you observe a transit, you're seeing the information as emitted from the planet. And so the planet, if you're modeling those two together, you often have to reconcile them. But also if you model the primary eclipse and the secondary eclipse together, you have to take into account the light travel time between them, or you'll bias your eccentricity. So when you include the star in your model, you get a physical scale, you have a physical model, and you can account for that. Okay, so I don't have time to go into all the detail. There's a lot to go into this, but I just want to give you a brief overview of some of the most popular exoplanet modeling software that are available. And these percentages that I'm showing here are the number of TESS discoveries that have used these codes, and sometimes the TESS discoveries use more than one. But this just gives you a good idea of the most popular ones, and I did this about a year ago. It was a lot of work to extract that, so I haven't redone it. But these are the rough values, and the ones on the left here are all Python based. They're very nice for people, especially when they're learning Python, and that's quite nice to build on. Exoplanet in particular is nice because it's built on PyMC3, which is very, very fast. But I think ExoFast, which I'm partial to, and is quite popular, is very nice because it includes the model of the star within the model, and you get that synergy between the stellar density constraint from the transit, and you can include all these additional effects in the model, like the light travel time, and you get precise stellar values too. So I'm quite partial to ExoFast, and I'll just leave it there. Thanks.
Thanks, Jason. Rounding us up, we have Andrew Vanderburg. Andrew is an assistant professor at MIT, and he's done some great work on analyzing tricky cases in Kepler and TESS data, leading to discoveries including planets around white dwarfs and new planets discovered with machine learning. And today he's going to talk about machine learning, especially as it applies to vetting planet candidates from TESS. Andrew, you're muted.
Oops, always going to happen. Thanks, everyone, and thanks, Megan, for the very nice introduction. I'm excited to be able to talk to you a little bit today about machine learning and exoplanet detection, and especially embedding. So now that Adina has taught us how to make our own light curves, and now that Rodrigo has taught us how to get all of the instrumental junk out of our light curves, we have a new task if we want to find exoplanets, and that is we need to search for transits in all of our light curves. And that's a lot of light curves, and TESS is producing about 1 million light curves in the full frame images brighter than about 13th magnitude every month. So that's a lot of stuff that you have to look through. So what you do is you do an automated search using an algorithm such as the Boxley squares periodigram, which goes through every possible orbital period for a planet, every possible time of transit, and every possible transit duration, and asks, is there a consistent transit-like dip at this period, duration, and epoch? And if the answer is yes, then you get a little spike in this periodogram, and that indicates that there might be a planet. And if you take a look at the light curve in this case, indeed, there looks like there's a relatively shallow transit around this star. So once you do this for all of your light curves, everyone that comes out of the TESS mission, everyone that comes out of the Kepler mission, there's a problem that we have to address, which is that planets are not the only things that cause stars to dim. This figure shows a couple of other things that cause stars to dim. One option is that you have some sort of other astrophysical phenomenon, such as an eclipsing binary, which is blended with your target star, which causes the light of the star to be a little bit fainter. Another option is that we didn't perfectly remove all of the instrumental systematics, and we get a slight dip in brightness caused by instrumental effects. And finally, there's the case that we care about, which is that you have a transiting planet. So for all of these many, many signals, we have to ask this question: are these signals due to a planet or a false positive? And making this decision for every possible planet detected can take a long time. In Kepler, there's something on the order of 100,000 signals that we would have to sort through to make this decision. And in TESS, we're equaling that every month. And over the course of the mission, we've built up a library of over 2 million possible signals that we have to decide planet, astrophysical false positive, or instrumental false positive for. So how do we do this? Historically, there are two options for how you make this decision. The first one is you throw human power at it, and you ask a team of vetters, usually who are experienced in this kind of analysis, to look at every single one of these possible signals and decide whether they think it's most likely a planet or most likely some astrophysical false positive. Humans have some very strong advantages, which is that we're really good at looking at new and unusual situations. We don't take many different examples to learn a new category. If we see a new type of phenomenon and we don't necessarily know what it is originally, we can look at that one and maybe a couple of others before we start to realize what category to put similar things in. And we're not very, we make very few easy mistakes. We tend to struggle on more challenging cases, but we don't often make completely boneheaded mistake. The other option is to use some sort of automated vetting or artificial intelligence. When I say artificial intelligence, I don't necessarily mean the Terminator. What I mean is that you use some sort of computer algorithm that's designed to mimic an intelligent decision, such as planet or not planet. The advantage of an automated system is that it can be faster. Computers can scale much faster than humans, and they can make these decisions really efficiently. And computers are also more consistent. If you have a human, two different humans on 2 different days might make a different decision based on what kind of day they're having, when the last time they had coffee, etc. Computers don't have this issue. So for the prospects of going through all of these signals, especially as we get more and more data from TESS and from other surveys, machine learning and automated vetting seems to be winning out. So that's what I'm going to talk about today. Recently, in particular, neural networks have become a really active field of research, trying to use neural networks, which are these cutting edge tools for object recognition and all sorts of other techniques that are being used in the computer science field. We're being able to apply them to search for transits in light curves and identify which signals are planets and which signals are false positives. The way they work is you have an input, which can be an image. It can be a one-dimensional image, such as a light curve. And you take the pixel values, you send them into this layer of neurons. These neurons do a mathematical operation on these pixels. Those mathematical operations are tweaked based on lots of different examples to try to minimize the difference between a set of known values and a set of known inputs. And as you keep performing these mathematical operations, eventually you abstract away the information in these pixels and have it turn into one number. In this case, a number 1 or 0 representing a cat or a dog. And in this case, the neural network gets the answer right. It finds that this is a dog sleeping here in this laundry basket. We want to do exactly the same thing, but instead of sending in pictures of cats and dogs, we want to send in light curves or one-dimensional images of planets and false positives. And hopefully our system that we implement will do the same thing. And it will take this image of a very nice planet light curve from Kepler and spit out a classification of planet at the end. This has become fairly common. And in fact, we're already using neural network triage to reduce human workload for vetting planet candidates from the MIT Quick Look pipeline. So if you work with any planet candidates from the MIT Quick Look pipeline after, say, sector 6 or so, they probably have gone through a neural network before coming to you. So once we've done this, and once we have this system to send these planets on without as much human effort as was needed before, we can then send Jason lots of nice exoplanet candidates so he can model them with ExoFast. And that's all I've got. Thanks.
Great, thank you, Andrew, and thank you, everyone. And so if anyone has questions for the panelists, we're using the hashtag data analysis channel on Slack, and I'll be monitoring that. As questions start to roll in, I might use moderator privilege to ask the first one, which is that I think that a lot of data analysis with TESS has been, the groundwork has been laid with Kepler and K2 analysis codes, and quite a few of our panelists have also worked on that data. So I'm wondering what the differences are when we as a community move to using TESS data, and what kinds of commonalities there are with Kepler K2 and what things we've had to adapt to. And I might ask Rodrigo to start because he's worked extensively on systematics modeling in K2 as well as TESS.
Sure. Yeah. Well, right off the bat, TESS systematics are a lot nicer than K2 systematics, which is where I developed most of my detrending software. So with K2, the roll motion on 6-hour, 12-hour timescales dominated most astrophysical signals. With TESS, I mean, like, you can find planets pretty easily without doing much detrending at all. There might be some background corrections. So TESS has scattered light from the Earth, from the Moon. There's noise on slightly different timescales, but in general, the magnitude is much smaller. And so detrending isn't as much of an issue. The other thing that's different about TESS, especially regarding the kinds of things that I've worked on, the linear models that I've worked on, is that fields tend to be more crowded because the pixels are bigger. And so something like Everest, which uses information at the pixel level and makes assumptions about, the target in your aperture is the only astrophysical source of light. So those assumptions break down, and something like Everest doesn't necessarily work out of the box for TESS light curves. In many cases it does, but it is an additional worry. And so like things like PSF modeling or deep blending become more important for TESS and need to be taken into account when detrending. I know that the other panelists have many other things to say as well. Those are just a couple.
Great. Jason, you look like you maybe have something to say.
No, I think from a from a modeling standpoint, if you have the data and it's nicely detrended from Rodrigo, then it doesn't matter much. I think the one major difference is TESS is producing a lot more single transit systems because the stare is much shorter. And that presents a unique challenge for the modeling when you don't know the period. So then the transit duration is much less known, and therefore the eccentricity and the stellar density and all that stuff is. But you can actually take a decent guess at the period just from a single light curve if you know the stellar density and if you can kind of assume that it's a circular orbit.
Great. So in that sense, the TESS continuous viewing zone is the most Kepler-like for you.
Yes.
Adina, would your TESS FFI extraction methods work on Kepler K2? Have you used them, or would there be differences?
So I haven't actually ever used Kepler data, but I have been told that everybody wishes they had Kepler data. So I assume that a lot of the stuff done in Eleanor would maybe be too much over detrending over background subtraction from Kepler, but I'm honestly not sure. With respect to K2, I think that some of the methods that we use, maybe like principal component analysis, which is those components are provided by the TESS team. If they were provided by the K2 team, would also be very readily implemented with Eleanor. But in terms of background stuff, I think I don't think it would translate very well.
Yeah, yeah, TESS definitely has more background, more complex background signal with the Earthshine and everything. Andrew, you've worked extensively on all of these missions. Do you want to add anything?
Yeah, I think that one of the biggest things that we've had to get used to with TESS is the idea that we don't necessarily know exactly what the transit depth is as precisely as we did with Kepler. Kepler, of course, had a tighter pixel scale and smaller PSFs, so it was easier to find clean background pixels, which Rodrigo also mentioned. That also means that you have an easier time getting the background levels estimated well, and you have an easier time deblending because there are just fewer stars nearby. So if you do this same kind of analysis and TESS, you have to be really careful that you know of all the stars that are contributing light and you get all of the backgrounds out, or your planets can be slightly too big or slightly too small if you haven't quite detrended everything out the way you expected. So that's kind of something that we were a little surprised by. Maybe we shouldn't have been surprised by it, but it came as a little bit of surprise when we started seeing that some planets were slightly different in depth from the ground-based observations that were used to follow them up, and tried to figure out why.
Great. We have a few questions in the, well, we have quite a few questions in the chat, but a couple of them are about the gap in the light curves, which comes from, presumably from TESS momentum dumps. Ayushi Rajgor was asking about this, and we also have a specific question about the gaps from Andrew Rosensweet, sorry. For Andrew about whether those dumps influence the convolutional neural network's false alarm detections. So maybe Andrew, you can start by addressing the influence of gaps for you.
Yeah, definitely. So in every TESS sector light curve, there's a big gap in the middle, and that's due to TESS coming close to the Earth, downlinking its data, taking a little break, and then downlinking its data again. And that is probably going to change in the extended mission too, as we heard from George. But every time you downlink the data and you turn towards Earth, you have a lot of scattered light nearby. So you often will get a period of time where the data aren't great. And that's usually what causes the gap in the middle of the light curve. And for sure, momentum dumps definitely are something that convolutional neural networks have to be trained to handle. And that's exactly what we do. So when we work on the convolutional neural network for TESS, Astronet TESS, we created a training set where we looked at lots and lots of different signals. And then a team of humans by eye went through and determined what we think each of those signals was caused by, whether it be an eclipsing system, a momentum dump, a stellar variability, like a pulsator or a rotator. And if you do that, you'll find that a lot of transit signals are actually caused by those momentum dumps. So by teaching it how to recognize those and tell them apart from the planets, we essentially take care of that. Now, as the momentum dump strategy changes because the TESS pointing is continually improving in time, because we're getting better and better at modeling this radiation pressure on the spacecraft, and we're getting better at flying the spacecraft. That slightly changes the momentum dump characteristics as well. So we may need to keep adding in new examples of momentum dumps so that the neural network keeps up to date basically on what the latest behavior of the spacecraft is.
Great, thank you for that clear explanation of the gaps. Does anyone else want to jump in?
I think Andrew covered it.
Okay. Let me see. So Jason, there's a maybe a quick question for you. You mentioned the lower limits in the statistical errors for different stellar properties like T effective, bolometric flux. Do you have a similar estimate for the stellar mass there? And if you did get a very small error bar on your stellar mass, how do you suggest that people deal with that? Should they just change the error bar on it to agree with the systematics?
Yeah, so that's a very good question. So roughly speaking, the error floors are actually quite complicated, and I'm sort of speaking from a solar type star. And in that solar type regime, the errors on the mass are about that same 2%-ish. But for low mass stars, they can be much larger, like 5% or even worse, depending on what sort of models you're using. And as for how you deal with them, it depends on how you're actually fitting them in the first place. So if you do the star separately, you get these tiny errors, yeah, then you can just inflate the errors to whatever you think is reasonable and then propagate those after the fact. If you do it in a simultaneous model like ExoFast does, we actually have these error floors built in, and what we do is we actually fit the parameter twice. We fit the parameter from this model that's over constrained, or that's too tightly constrained, and then we sever that connection from that model and the rest of the model, and then we connect it again by adding a penalty between the model parameter that we get that's too precise and the model parameter that we care about, and then we add what we think is the systematic floor. So we just add it like a prior. We say the model parameter constrained from the SED minus the model parameter that I actually care about divided by the systematic error, which is 2% or something like that. And that's how we propagate that within a global model.
Great. Does anyone else have any comments about systematic errors? This is definitely not unique to stellar parameters. I think in many cases, these systematic errors that we've been talking about are explicitly modeled in the TESS data, as Adina and Rodrigo especially were talking about. So that's one connection there. But I suppose that if you don't get your systematic model quite correct, then you could have many different kinds of issues in the subsequent data analysis.
Yeah, the real difficulty is when you don't realize what your source of the systematic errors are. Like in the stellar models, we know something's wrong, but we don't know what. So it's really tough to account for that.
Right.
I'll echo what Rodrigo said, which is that it's way better than it was for K2. So we're all very happy about that. We don't have to worry nearly as much about systematics as we did back then. Great.
Moral of the story, always pack extra reaction wheels.
Exactly.
There seems to be a lot of interest in machine learning, and we have one question from Dave Ciardi for Andrew Vanderburg, although I think other panelists have also used machine learning, so could also jump in. David asks, as always, the main issue with AI/machine learning is the training set. So can you talk more about this and how to best characterize the limits of the AI within the context of a limited training set?
Yeah, that's a really hard problem to answer, because in general, in astronomy, we don't have a gold standard. We don't have ground truth. We can't fly to these systems and figure out if there's actually a planet there, or if that signal that we see is a momentum dump in general. So we have to kind of rely on our experience. We have to rely on, using longer data sets where we're more confident to train using little small segments of data sets if we want to really push down to like the low signal to noise regime. It's also a problem because when humans create training sets, we don't do it perfectly. What we found when we were working on Astronet for TESS is that when two different vettors, say for example, when Chelsea Wong and I each looked at the same set of signals, we only agreed about 90% of the time when we were doing it independently on our own. And then when we kind of came together and we looked carefully at them between the two of us, and we often would come to a consensus, and sometimes I would be correct and sometimes Chelsea would be correct, and we would agree with one or another of us. So our strategy there modified a little bit into a large number, 3 or 4 people all looked at the same signals, and we only agreed on this kind of first round if all 4 of us agreed and said the signal was the same. And then if we didn't agree, we would come and look all together in a group vetting session. So that seems to have helped the accuracy of that training set. But you're always going to still have mistakes. You're always going to still be limited by the accuracy of your training set. And that hurts you both in terms of the neural network being able to train, because it's trying to mimic a human who is flawed and who will make mistakes. So it may end up making similar mistakes, but also by your ability to evaluate it. Because if the machine learning system gets everything 100% correct, but the ground truth sample, the training set that we're using or the test set that we're using has 10% errors, then you'll never do better than a 90% accuracy for your machine learning system. So yeah, that's a big challenge. And all I can say is that the answer is to try to use these tricks to make your training set as good as possible and your test set as high fidelity as possible.
Anyone else want to weigh in?
I can chime in a little bit. I think some of the biggest limitations for TESS is the changing background and systematics from each sector. And so I developed a neural network called Stella that identifies flares in test data that was trained on Max Gunther's sectored 1 and 2 flare catalog. And now that he is running that on all of years 1 and 2, we're seeing lots of issues identifying, background as potential flares because it hasn't seen those examples before, or really massive flares, only a few minutes apart that just weren't in the original examples. And so I think, all of the limitations that Andrew just talked about are totally true. And I think one of the things that we need to think about moving forward when applying machine learning is like transfer learning, or continuing to retrain parts of your network on new examples that we're seeing. So even like the momentum dumps that Andrew was talking about, new systematics, new, if we're finally seeing like many stars with fast rotation periods that look kind of peak-like, kind of like flares, retraining on lots of those examples to just get the neural network to identify those as false positives instead of true positives. And I think this is also really relevant, not just in the context of TESS, but in the context of all of the future missions that will be coming online, like LSST and Roman and stuff like that. So I think that's what this field needs to start thinking about for the future.
Yeah, that's a great point. It'll be very interesting to see how all of these systems handle the ecliptic mission when TESS is now pointed sideways and there's going to be more scattered light.
Adina, can you say a little more about how the training sets change from sector to sector and cycle to cycle?
Yeah, so it definitely depends on how you're building your training set. Andrew, it sounds like your team is using the full light curves. For the Stella one, we use like smaller chunks. So only about 200 cadences per example in the training set. And so you really only get localized information about the systematics from the test background. And so I think maybe that's one of the biggest flaws in the neural network that I developed, but I think it also provided a new interesting way to kind of characterize flares in terms of probability. So I think there's a lot of wiggle room and exploration that can be done in terms of what you want to feed your neural network, how many cadences you're feeding it, if you feed it the whole light curve, if you feed it one orbit at a time, if you feed it a few cadences, even if you feed it the image, what can you get out of the image data that you're missing in the light curve data. So I think that a lot of us here have explored the 1D option, but not as much the 2D image option. And so I think that there's a lot of room to still play with that.
I love that, going to the 2D and taking full advantage of all the data that you have. Sam Quinn asks towards Andrew, you talked about the difficulties in knowing ground truth, especially for small planets and low SNR. He wants to know, can we hope to get closer to ground truth for training sets using the K2 planets viewed in the extended mission?
Yeah, that's definitely a really good idea. We know that there are signals there because we've seen it with a 1-meter telescope, even if they're relatively low signal to noise in a 10-centimeter telescope. So that's a really good way to get a bit closer to ground truth. Of course, we still can't fly there. We still can't determine exactly whether those are planets or not, but with much better data from K2, we'll be able to have a lot better idea, especially at the very low signal to noise. The other way would be to do something like what Adina was saying, which is where you take a multi-planet system that you've observed for an entire year at the continuous viewing zone, and then you only show it small segments of the light curve. So if you have 50 total transits and it gets you to signal to noise of 15, you could chop that into 10 transits here, 10 transits here, 10 transits here, which all get you to a lower signal to noise.
So I see that John Doty had the same question that I had. He says, can you incorporate information from follow-up into your ground truth? So like after you've confirmed a planet, can you go back into your training set and say, yes, this is a great planet, or if you've identified as false positive, you can take that out of your training set or identify
Yeah, definitely. So Dan Moldovan in the machine learning splinter session yesterday, he has a poster about the TESS the TESS neural network for triage. He was also talking about how we could feed in this ground truth information once we've confirmed a planet from the ground as kind of even higher weighted information in our training set, so that we can ask the neural network when it's training to prioritize these planets most highly because we know that they're real. The other thing we're thinking about doing is testing whether or not we can use follow-up from the SG1 group to determine if signals are on target or off target, to figure out how to interpret difference images better. Because when you're looking at difference images, it's hard to tell for sure whether you're on target or off target to better than about a test pixel, just because we start losing resolution, even though the information is probably there, because you can see how the PSF shifts just a little bit in the difference image. But without a ground truth, it's really hard. So SG1, with their much higher spatial resolution, especially from the LCO nodes, could really help us out there by giving us this independent set of very definitive on target, off target with higher spatial resolution than we can hope to get with TESS.
We have a question from Thomas Wilson, which is directed at Adina. He says, great work at the FFI on the FFI pipeline. What do you think are the next advances that could be done for extracting data from FFIs, especially going into the future with shorter cadence FFIs? And I think the general question of how does more and faster FFIs change the picture could maybe be applied to other panelists too. So Dina, if you want to start us off there.
Yeah, I feel that a lot of the methods that a lot of the teams in the community have used are all great. And so I think that even that applied to the faster cadence FFIs, I think they're going to be fine. One of the biggest concerns, or not concerns, I mean, I'm grateful for the 200-second FFIs, but, you know, a little bit of a panic attack when you hear that, is just the amount of like storage space we're going to have. So things like the difference imaging pipelines, they have to download all of those FFIs to create their light curves. And so is that still going to be accessible to a lot of the members of the community? So one of the things that I've been thinking about is, you know, Eleanor behind the scenes uses TestCut, which is a great tool that is provided by MAST. And so what that does is it cuts out smaller regions of the FFIs. If that tool is going to be accessible for the 200-second FFIs, you know, I think that would be a great way for teams to still be able to do their reduction pipelines and access that data really easily. So I think in terms of the methods themselves, they seem pretty stable to me. I think they're going to do just fine. But in terms of, you know, just data access, I think we're going to have to think a little bit more about, you know, how different teams handle the amount of data. And I don't want to like pawn it off on MAST because they're doing an already awesome job supporting us. But, you know, if they're going to continue to do this, I think, you know, we as like the FFI teams need to have conversations with them about how to best interact and make sure that we're not going to break down, you know, their code and cause like issues on their end.
Yeah, that's an interesting point because so many areas of astrophysics are going to have to deal with the problem of, or are already dealing with the problem of too much data too fast.
It's a good problem to have, I guess.
Yeah, definitely. It's better than some problems.
So I think that one thing that we can be excited about for the 200-second FFIs is our ability to correct systematics. So in K2, the systematics were caused by this slow drift of Kepler over about 6 hours, and there was not really much going on timescales faster than an exposure time. And that's kind of the opposite of TESS. The dominant TESS systematics, these momentum dumps, are caused by really fast oscillations, just a few seconds. And that broadens the PSF and changes the response on the detector. The faster our observations, the faster our data sets, the more effectively we can actually correct those fast oscillations, because otherwise we're kind of smearing out all of the information that's needed to correct the systematics. So I would expect that if you took a 200-second TESS light curve, corrected systematics, and then bend it to 30 minutes, you would do better than you can with a 30-minute FFI that you just corrected based on that information. So I'm really excited about the potential precision boost that we'll get from the 200-second FFIs, in addition to just the faster sampling.
Yeah, the same was true for K2. When you detrend a short cadence K2 light curve and repin it to long cadence, you do noticeably better.
Yeah.
The same reason.
All right, we're coming up to the end of our 50 minutes, but thank you all so much for this great conversation. We have quite a few more questions that we didn't get to on the Slack, and so if people want to go there and answer things or continue conversations at their leisure, it's again in the data analysis channel. And so thank you so much to our panelists, and I also just want to highlight all of the hard work that that you and many other people have put into making these software tools accessible to the broad TESS community. I think it's made a huge difference in the amount of science that's coming out. And it makes me very happy to be part of this community. So thank you all. I'm going to turn it over to Max Gunther, who is our host for the rest of the day or morning.
Thanks, Megan.
Thank you very much again, Megan. Thank you to all the panelists today. It was really enriching and interesting discussion. And we're now diving more into some talks on data analysis. And just to briefly introduce myself as the chair, I'm Max Gunther. I'm currently a Torres Fellow at MIT, working with TESS on flares, exoplanets, and chances for life. And I'm in transition to a new role as a ESA Research Fellow at the European Space Agency based in the Netherlands, where I'll start in a few weeks. And with this, we'll start our session. I just want to remind you, this is about data analysis. We cover a wide range of topics today. We have 3 talks currently, and then we'll head into Gathertown for some posters, and then we'll have 2 more talks in the afternoon session. Please ask any questions you have in the Slack channel, so don't post anything in the Zoom chat, but everything please go to the respective Slack channel, and then after the talk, I'll read those questions out. Each speaker today has 12 minutes for their talk and 3 minutes of Q&A time. For all the speakers, I'll interrupt you after 10 minutes very politely and to give you a 2-minute warning. And after your 12 minutes, I'll interrupt you again to come to conclusions. And after 15 minutes, I will impolitely interrupt you, and we'll move on to the next speaker. And with this, I have the pleasure to introduce Jeroen Audenaert, who's going to talk about test data for Asteroseismology, TDA, Stellar Variability Classification Pipeline. That's an invited talk. And with this, Jeroen, please take over.
Thank you for the introduction, Max. You should be able to see my screen now, hopefully.
Yep.
So great. So my name is Jeroen Audenaert, and I'm a PhD student at the KU Leuven Institute of Astronomy, based in Belgium, and I'm specifically working on machine learning for TESS. Today, I will talk about the TESS data for Asteroseismology, Stellar Variability Classification Pipeline, which is a part of the larger TESS Astroseismic Science Operations Consortium. So, as the name says, the goal is to classify the stellar variability that is observed by TESS based on light curve information. Because there are so many millions of stars observed by TESS, it's practically impossible to manually go through all of these, light curves by hand, because this would take a lot of time. So therefore, we have built a machine learning pipeline that can classify variability based on the light curves. And Here we are interested in a lot of different types. So we classify the pulsators, but also eclipsing binaries and rotational variables, which you will see in the next slides in more detail. Now, the TEDA variability processing pipeline actually comprises multiple modules. The first module is the photometry module. And here we go from the images to the actual light curves. And in the next one, we do corrections using two different methods, a CBV method and an ensemble method. And then the third one, the classification, that's my focus for today, where we actually classify all light curves down to a test magnitude of 15 that got processed by the previous modules and classify them according to their variability type. In case you want to learn more about the previous two modules, you can see the talk by Derek Busazi in the TESS FFI Splinter session. Now, here you can see a graphical illustration of what our stellar variability classification pipeline looks like. We're actually classifying at two different levels. So we first do a top level classification, and that will be the focus of this talk today, where we classify light curves according to their general high level variability classes. So these include solar-like pulsators, transiting planets and eclipsing binaries, or Lyrae Cepheids, gamma dors, delta scutis, and so forth. And in the next stage, a second level classification, we also use additional information, such as color information, to classify these classes into more depth. And here we also use unsupervised machine learning methods, while in the top level classification, we use supervised methods only. And we actually combine multiple separate classifiers, as I will detail in some of the next slides, and combine these to come to an optimal prediction. Now, here you can see what our training data looks like. So we started from a labeled set of Kepler Q9 data, and we truncated all the light curves into 27.4 days in order to mimic the test duration as good as possible. Our training set comprises about 8,500 stars, and here you see the classes again, and underneath in gray you see the number of stars for each class. All of those stars, except for the constant stars, are real data, so it's all from Kepler, in order to really capture the instrumental characteristics and get a good idea of the accuracy that we will in the end get. You'll see that the number of auroral Lyraes is a bit lower here, but this is just because not too many stars of this were observed by Kepler. Here you can see a couple of examples of each of 4 light curves that are present in those classes. So on the left, you see the light curve itself. On the right, you see the amplitude spectrum. So we use information both from the time domain and in the Fourier amplitude spectrum, because sometimes it's much easier to just look at the light curve itself and discriminate it from other types of variability. But often it's also easier to just look at the amplitude spectrum to discriminate different types of stars. Now, our classification scheme, as said, we use multiple classifiers, all of those machine learning classifiers. What we do is we combine their predictions by means of a meta classifier, and more specifically using stacked generalization. And this allows us, by combining multiple separate classifiers, to come to optimal conclusions. So we have all the light curve data, and what we then do is, depending on each classifier, we generate different features. So these are statistical attributes that are used to characterize the light curves, and that are then used as input and make the classifier decide which type of variability we're dealing with. So SLOSH is the first classifier, and this one just uses an image-like representation of the power spectrum, and based on that predicts the variability classes. And then for the other 3, we have a sorting head, GBGC and RFGC, and 2 of those are random forest, and 1 is an XGBoost method. And here we only use features. So for example, this can be the first dominant frequency or the skewness, which I will show more in depth in the next slide. Now, each of these classifiers predict probabilities. So we get 8 times 4 probabilities. So for example, for a certain star, SLOSH predicts an 80% probability of being a solar-like oscillator, 0.1% of being a constant star, for example, and so forth. And then we get a prediction for each of those other classifiers as well for that same star. And we combine all of these by means of a meta classifier, which is also random forest, and then get a final estimate of what the variability class should be. And so these are probabilities then. And by having all these classifiers, we can really leverage the strength of each individual classifier and get the best possible results. Now, the features that we're using in each of these classifiers, you can see a couple of examples for them here. We're operating in the Fourier domain, so each of these classifiers is usually using distinct features. So some of them are using the first frequency, the second frequency, third frequency, and so forth. And then in the time domain, we also use the skewness in certain classifiers, which is very good for finding eclipsing binaries, for example. Or in the entropy domain, we are using metrics like the multi-scale entropy, which actually assesses the regularity of a light curve at different time scales. And this is just measuring the some type of complexity or stochasticity. You can see a couple of examples. A multi-scale entropy, you get some type of curves that are here, and we then characterize these by means of the standard deviation, the mean of the curve. And these are then used as input attributes in one of the classifiers. And lastly, we also make use of a sum in one of the classifiers, the individual classifiers. This. Now, here you can see the feature importances of the meta classifier. So we calculate how important each probability that is given by the individual classifier is in making the final decision by the meta classifier. And I'm just putting this there to really illustrate the importance of having the multiple classifiers. If you just look at the top, you can see that the first most important feature is slosh, solar light probability, then the sorting hat classifier, next RFGC, and next GBGC. So we see that each classifier really contributes a significant amount of information towards this final prediction. And the meta classifier can really leverage the strength of having all these different probabilities and thus really coming to an optimal prediction here. Now, to show some results, this is the confusion matrix we are getting. So this is based on labeled Kepler-Q9 data truncated to 27.4 days. And here we get a 94.9 accuracy in total. And this ranges for individual classes. We see for gamma dors and SPB stars, we get about 90% classification ratio or recall rate here, to even higher for transiting and eclipsing stars and planets, and even higher for constant stars, 100%. So overall, we're getting good classifications, as you can see. Now, we also applied it to TESS to get some first insights already. We will release the classifications later on in the year. But the first insights we got right now is that we trained our classifier on Kepler data and then applied it to TESS. And we see that we're still getting relatively good performance. Now, this is good news that even though it's trained on a different survey, we still get okay performance on TESS, which is very nice. But the challenge is that we still have to deal with different instrumental characteristics that are present in the TESS data, and we're not in our training set, of course. So therefore, we can see, for example, that certain instrumental events that are happening get classified all as eclipsing binaries. So this is something we are working on right now to actually make sure that our new training set takes into account these specific instrumental characteristics of TESS. And the way we're doing this is we're using the results we're getting from the Kepler trained classifier to actually construct a new training set on TESS using an iterative process to just come to this best training set, and then in combination with known labels. Now, we're also working on classifying the Kepler field of view in TESS because we already have much more information here. So this will give us a good estimate of how well our classifier is doing as well. And then in parallel, we're now also starting to work on classifying all the TESS data. So hopefully we can do this in some of the coming months and release these. Now, to conclude, we are using an ensemble of strong classifier here using stacked generalization. Now, the strong classifiers mean that each classifier tries to predict a certain variability class as good as possible. And yeah, the ensemble is just that we combine all of those. And we can really see that there is a significant improvement by using the meta classifier than in case we would just use one single classifier. And we get a 94.9% accuracy. What we also did is already classify the 160,000 stars that are in Q9 based on 27.4 day data using our classifier already. And we can see that here we get a performance that is similar to the training set actually. So, and then lastly, what is very good news, the first application to TESS already looks very promising, although we still have to do some work on there to optimize it. We're still getting good results already. Thank you.
Thank you very much, Jeroen. Give a round of applause for everybody in the audience, all 240 people. Really nice talk and right on time even had like a spare minute, so we have more time for questions. And we're starting right off with a question by Chelsea Huang. When you classify Kepler field of view using TESS data, how do you plan to deal with blending issues? Because the pixel sizes will be very different, correct?
Yeah, these will indeed be different. So we're still working on that part actually at the moment. We haven't yet done the classification itself, so I'm still trying to see how exactly we will take this into account. So this will indeed be a challenge to see how this happens.
Yeah, that goes hand in hand while somebody else is typing a question right now with a question I had. Like when training on a different data set than like the one you're validating on, so training on Kepler, applying it to TESS, I'm actually surprised to hear that it looks very promising and very good, because the systematics are very different, the time spans are very different, the precision of the instruments are very different. Can you elaborate a little bit more on this, what you've seen so far?
Yes, so that was indeed a very pleasant surprise for us as well, because yeah, the systematics are indeed very different. So it really depends on which classes we're looking at. For some classes, for example, for the pulsators, we could see that the accuracy was rather good, and those classes those variability classes got high accuracy. But for other types of classes, for example, eclipsing binaries, we could see that because we took a sample from the first sector of TESS, and here we also still had fine pointings of the satellite, which actually appeared as large dips or increases in brightness in the light curves. And we saw that these light curves, because we trained on Kepler data, actually got classified as eclipsing binaries. So that's really one of the challenges, because it was trained on Kepler and then applied to TESS. Of course, yeah, we haven't captured these type of instrumental characteristics yet. So this is, of course, yeah, that part is still really something we are working on right now, and therefore, of course, we want to construct a new training set based on TESS data, and we're doing it in an iterative way, because when we can already find some predictions that are correct by the classifier right now, we can just save those, retrain with them again, and then keep on doing this together with already known and published labels for certain types of stars. And this should then allow us to come to an optimal result on TESS as well with a new training set.
Yeah, thank you. A question from Michael Foss now. The labeling for TESS, is that for FFI light curves or for 2-minute light curves, or does it even matter?
So we will right now, we have used on the FFI light curves. But we've used the 30-minute light curves, I think. But we're going to do all of it. And in case you want to get more information about which type of stars we're processing, you can also go to the light curve splinter, where each of the different types of light curves that we will process will be detailed.
Great. And another question by Monica Jurkovic. How will you separate the RR Lyrae and Cepheids or other different subtypes later on?
Yeah, so we will do this by adding more attributes as well. So for example, color information, so just not purely based on light curve information only. So
are you going to implement this in like the full pipeline run, or is this going to be a separate classifier afterwards? So
we're still debating on the exact setup of this, but we'll just use the predictions we have already from that general level 1 classification. And then by adding attributes, probably either train a new classifier and use this in combination with unsupervised clustering, then run it based on this and get the results of more of these separate subclasses.
All right, perfect. And I see somebody else is typing. We have like about 30 seconds left, so you can take any remaining questions in Slack, but I want to ask one more question, namely, how good is like the pipeline? Oh no, actually we have it now. George Ricker is asking, will you be able to retrain on sectors later than 1 and 2? As you may know, the pointing system characteristics for TESS were dramatically improved in sectors 4 to 5.
Yeah, exactly. So we will be able to retrain, and that's really the goal of constructing this new training set as well, to be able to deal with, if we have better accuracy and we don't have those issues with the pointing, then we can get better accuracy as well if we retrain on the other sectors.
All right, perfect. Well, thank you so much, Jeroen. And we'll give a round of applause on behalf of all the participants again. And with this, we have Belinda Nicholson coming up. Belinda, if you want to start sharing your screen already. Belinda is going to speak about the physical interpretation of quasi-periodic Gaussian process models for stellar activity. A very nice topic that we're all interested in. And please take it away, Belinda.
Fantastic. Thank you very much. So hi, everyone. I'm Belinda Nicholson, and I'm a postdoctoral research assistant at the University of Oxford, a junior research fellow at Somerville College in Oxford, and an adjunct research fellow at the University of Southern Queensland. And today I'm going to talk a bit about some of the work I've been doing with Suzanne Agren at Oxford on trying to understand what we can learn from the quasi-periodic kernel Gaussian process study of stellar data, and whether or not we can get anything meaningful out of this, anything physically meaningful out of this. So why do we care about quasi-periodic kernels and doing Gaussian process modeling? Well, it all comes back to trying to understand better stellar surfaces. So stellar surfaces are not uniform. They have spots like this beautiful illustration of the sun. So this is images from SDO of the sun, and you can see it's spots that come into and out of the line of sight as the sun rotates, and they change over time. And our sun, like other stars like our sun, also behave the same. And this impacts the data that we get. We can see variations in light curves, and we also see variations in the radial velocity data. And if we're wanting to then search for planets that are on small signals, that have small signals, we need to better understand these stellar surface signals. And one of the ways that is quite popular at the moment, and is very useful, is to use Gaussian processes as a way of modeling stellar data. So Gaussian processes are a very powerful and flexible analysis technique for time series data. Among other things, they're very useful for any sort of correlated data, but particularly in astronomy, it's useful for time series data. Now, I'm not going to go into a lot of detail about Gaussian processes. There are some wonderful resources out there, and some great talks by people that you can find online that will explain the nitty-gritty of Gaussian process regression and exactly what it is. But for the purpose of this talk, the thing that I want you all to focus on is that what we're not doing here is we're not fitting a function to data. Instead, what we're doing is we're defining our data set as a multivariate Gaussian. So each point in our data set is a dimension of our Gaussian, and we're fitting the correlation between data points. What we're looking at is trying to find a way of describing how one data point is correlated to the next data point in our time series. So a particular popular choice for stellar data is the quasi-periodic kernel. It's a kernel, so this is the function that defines the correlation between data points. It's the function to describe the correlation. This quasi-periodic kernel has both a period element, so the stellar rotation period, but also has some sort of evolution term in it as well as the squared exponential term on the right here. And we have various parameters in this quasi-periodic kernel that we can play with to try and get it to fit our data nicely. Now, these do fit stellar data very well, and they're incredibly useful, whether or not these hyperparameters, as we call them, because we're not fitting a function, it's not function parameters, we're fitting hyperparameters because we're not fitting a function to the data, technical. So these hyperparameters, as we call them, it doesn't, to some extent, it doesn't really matter if they're physical or not, because they're useful. But it would be cool if we could get something physically meaningful out of them, particularly with the period. I mean, so the period we know from previous work, for example, studies by Ruth Angus show, we can get information about stellar rotation period from the period in the quasi-periodic kernel. But what about the other parameters in this kernel? Can we find anything physically related? Do these relate to any sort of real physical phenomena on the star? In particular, does the evolution length scale here correspond to what sort of parameters of spot evolution? And then what about our harmonic complexity or the amplitude, for example? Do they correlate with anything physically meaningful, or are they merely a function of the data that we get, or systematics? So to start with, to answer these questions, we need the answers. We need a nice stellar model where we know what the answers are so that we can compare with what we get out at the other end on our GP.
So for this test, for this experiment, we've taken a stellar model. We've got 100 of these mock light curves and radial velocity data sets that span 250 days and are sampled twice per day. We have flux calculated by the formalism of Doran 1987. It includes some term of linear limb darkening. So it's a fairly simple but not too unrealistic stellar model. And we have various parameters of average spot number, stellar rotation period, a decay time scale, and we have some sort of spacing and size of these spots on the stellar surface. And then for the radial velocity, we calculate that as the contribution or lack thereof of the spot to the rotational velocity and the contribution of the convection. So inhibition of convective blue shift also comes into calculating what sort of shift in RV is caused by the spot on that surface. So with this, I'll just show you a couple of examples of the types of curves we have. So this is model 55 and model 84. I didn't give them names because there's too many, but anyway. So this just sort of shows you the types of curves that we're looking at and the types of variations we have within our data set. So we have our data set, we have our quasi-periodic kernel GP, and we now run this GP on our light curves and see what we get back in the end. So this shows firstly up for the light curves, for our light curves only, what we get for the period. Well, as we'd hoped and expected, we recover the period perfectly. In fact, the one-to-one line is so flat. I've got the residuals here shown on the right. So you can see that there is some more scatter as you get to shorter periods. This makes sense because we're getting near to where we're sort of sampling the data more poorly. We've only got 2 points per day. So for the very short rotation periods, you're not going to see, you're not really going to be able to resolve those as well. But certainly for the longer periods, we do very well. So that's good. We sort of already knew that was going to happen. But what about for some of the other parameters? So for the spot evolution time, we see that correlates very well with the QP-GP length scale. So this is the parameter that defines that squared exponential term at the end. And interestingly, in the way that we have defined our spot evolution and behavior in our stellar model and the way that we've defined our length scale in the GP, they correspond one-to-one with each other. Things to note also on this plot. So I've got a vertical dashed line, and that's the 250-day mark. So that's the extent of our time series data. Now, we do have some spot evolution times, some length scales, input spot evolution times that are longer than that. And we can see that past that point, it doesn't really fit so well. There's much more scatter to the data. In fact, it also almost seems to plateau at that point. It's sort of, the model doesn't try and push it up any higher because it sort of realizes it can't really tell much more than that at the 250-day mark. So those were nice, clear, easy, yes, nicely correlated, fantastic. We can tell some things about stars from this QP-GP, but what about some of the other term, the harmonic complexity? Well, this is where it gets a lot more messy. I've shown here both the stellar rotation period and the input spot evolution time. And while the harmonic complexity correlates with it, so if you've got a smaller spot evolution time or a slower rotation period, you're going to have a smaller harmonic complexity value in the way that I've parameterized it here. But apart from that, you can't, it's not like we see a nice clear linear relation like we did with the others. Also to point out in here, you've got this flat line up the top of values, and that's where the harmonic complexity has reached our upper bound. So we do set bounds on all of our values. We either set a uniform prior or an upper bound. This is important, particularly for the harmonic complexity. Otherwise, it can just keep climbing higher and higher, and that's where you get the difficulty of you might just end up fitting to the noise or just fitting to individual points rather than to some sort of functional form, or actually fitting to the form of the data. So having that upper bound is important, but yeah, here you can see that sometimes it will just want to just push to that bound. So that's for the light curves. What about for our radial velocities? So here we have our radial velocity on the x-axis and our light curve recovered values on the y-axis. And just like we saw with the input and output, we're getting some lovely, beautiful agreement with what the radial velocity GP finds and the light curve GP finds. They both agree on the rotation period, and they agree very well also on the recovered length scale. Again, I've got that dashed line at that 250 days. That's the limit of our data set. And there's a lot more scatter past that point, but you know, that's to be expected. You can't expect the GP to know more than if we don't give it the information to be able to infer it.
Belinda, you have 2 minutes left.
Thank you. So the figure on the far right, though, is messy, but also that's quite interesting. So we do not get agreement between the recovered gamma, so this is our harmonic complexity, between the light curve and the radial velocities. In fact, the radial velocities are systematically higher in gamma than the light curve. So this, again, somewhat expected in that the radial velocities can behave like the first derivative of the light curve. So you're going to get a higher complexity in the radial velocity data to the light curve data. But this goes to show that if you're using light curves to define your GP, your beautifully sampled light curves to define your GP, to help with activity in your radial velocities, you need to be careful that that harmonic complexity, that gamma value, is going to be different. So that just brings me to my summary. So the summary of this work is that we can recover well rotation periods and spot decay information. These things we can get out of a quasi-periodic kernel GP. But the other parameters, it's unclear whether or not they really have physically meaningful information in them. And certainly there's much more study to be done. There's a few more things that I'd like to test to see whether or not I can really understand better the way those parameters work. When it comes to comparing light curve and radial velocity GP solutions, they agree on rotation and evolution length scale. So feel free to use your light curve results as a prior on your radial velocity GP, but the harmonic complexities, that gamma term, will be different. And it will be systematically higher. It is likely to be systematically higher. And stay tuned. This work will hopefully be on the archive in not too long. And also some more things that I need to look at are injection tests to see just what happens when you put a planet signal in there, and also the effects of time sampling. This radial velocity data is what you'd have if you put a Nichelle spectrograph in space and was able to get infinite and perfect and amazing radial velocity data, but unfortunately we can't do that. So definitely looking further, I've started looking further at the impacts of time sampling on that. And if you're wanting to hear about that, then I'm happy to talk about that later. But that's all for now. Thank you.
Brilliant. Thank you so much, Belinda. I'll applaud again on behalf of all our participants. And we have a bunch of questions in the chat already and a lot of positive comments. This is really cool, says Rodrigo. And Keaton Bell asks, how well can JPs characterize a spotted star with latitudinal differential rotation?
That is a really good question. That is not something I've looked into. We've specifically chosen no differential rotation on these for these particular tests. Yeah, that's tricky. I'll have to get back to you on that one. I think that's another thing to add to the future work.
Great. Yeah, and always feel free. There's a lot of questions. We can't cover everything. Feel free to leave comments in Slack, or please be encouraged to. Ben Monte asks, the quasi-periodic kernel builds models with a singular inferred period. Have you explored how much, well, it's again, differential rotation does or does not affect your inference of stellar parameters. But I think going a little bit further, it's in line with like something I wanted to ask, do you think there's like room for having like 2 GPs run at the same time or something like that, or adding like a few more components also to one, like taking care of systematics, for example, the other taking care of the stellar aspect, or do you think it will be hard to differentiate between those?
Yeah, that sounds, it's worth a go. Yeah, I think that's the idea of adding an extra GP is like, oh my gosh, that's so much computation. But yeah, that's, I think that would be interesting to explore. Yeah. And certainly, so particularly for this particular GP, I also add a jitter term. So this is sort of exploring exactly what isn't covered in the GP. It allows my particular fit to sort of go, okay, well, I can't quite cover all of this information, so let's fill an extra jitter term. So maybe actually exploring more about how, what combinations of kernels, in fact, exploring different kernels as well, exploring how combinations of kernels could actually do better. So yeah.
Brilliant, thank you. We have 5 more questions that we couldn't get to, but please answer them in the Slack. There's a few with overlap, a few I'm really interested in, especially about like what optimization, MCMC or nested sampling, what priors, etc.
Yes, exactly. Yeah, sorry, I didn't get time to get into all of those details. Yeah.
But thank you so much again for a wonderful talk, and we'll look forward to your answers in Slack. And next up, we have Cretignier, who's going to speak to us about how to deal with perturbing signals in radial velocity follow-up. With this, please feel free to share your slides, and I'll hand over to you, Michael.
Okay. So, perfect. Hello, everyone. So my name is Michael Cretignier. I am a last year PhD student here at the University of Geneva. And today I will present on how we can deal with perturbing signal in radial velocity follow-up. So first, I would like just to remind that there is several ways to discover exoplanets. So here you have, and all the method leads to different observation of your exoplanet, like the radius or the mass. But all the methods are also differently sensitive to the planet that you try to recover. And today I will mainly focus on a Hertz-like planet or super Hertz planet. And if you look at that diagram, planetary mass versus distance to the star, you see that there is 3 main methods, which are the transits, but the probability of transit at a long period is small. Microlensing, which could work, but microlensing, it only works mainly in one direction of the Milky Way toward the galactic center, or the radial velocity with the next generation of spectrograph. Now, if I focus on radial velocity, if you look all the detected or discovered planets by radial velocity so far, you will see that there is a kind of saturation. We don't detect exoplanets below 1 meter per second, or we really hardly detect them. And if you wonder where a Hertz-like planet around the solar-like star is on that diagram, it is there. So you see that it is really one order of magnitude out of what we can discover today. If you want to understand why it is so hard to discover those planets below 1 meter per second, you have first to go back on what is a radial velocity point. In fact, you have 4 components on a radial velocity point, the exoplanet that you try to detect, and 3 contamination at least. On one hand, you have the instrumental systematics. On the other hand, you have the fact that you observe from the ground. So you have some contamination from the Earth atmosphere. And finally, you have also contamination from stellar activity because you observe the star. And I will begin with how we can deal with stellar activity. So I think it has been well presented in that paper of 2017 by Davis et al., where they clearly explained the main idea of what we can do. And the idea is that if you have a planetary signal, the planetary signal is inducing exactly the same radial velocity shift on all the line, because it's really a chain of the barycenter of the star. Whereas when you have stellar activity, each line will be individually affected based on the atomic properties of this line. So it can be because of Zeeman broadening, it could be because the line is changing because of temperature fluctuation in your stellar atmosphere or so on. And so based on that conclusion, my supervisor, Xavier Dumusc, proposed actually that we were trying to really measure the line-by-line radial velocity. So not to measure the radial velocity using all the stellar lines, as is commonly done with the CCF, but really looking each individual line. And he demonstrated, for instance, on that famous data set of really highly active star with a peak-to-peak of 10 meters per second on the CCF, that if you look some individual lines, for some lines, you have a really strong signal of 50 meters per second. If you look other line, you don't see any activity signal at all. And if you look other lines, you even have a negative amplitude, if you want, of the activity signal. And the first thing that you may try to do is simply to group lines or to only select the unsensitive lines, which is what we did at the bottom. And by doing that, for instance, you can already correct for stellar activity quite well. Now, talking more about instrumental systematics and the Hertz contamination, the first question that I would like to answer is first, is there really a problem about instrumental systematics today? In fact, I would like to argue that yes, we have a problem. I show you here an example of a star really highly observed by HARPS, 300 of data points. And if you look the periodogram, you have a clear signal at 300 days with a signal, a semi-amplitude below 1 meter per second. And so the first question that you may ask is, did I just discover a super Hertz in the habitable zone of my star? And in fact, the answer is no. What you just discovered is that you have an instrumental systematic which is producing such amplitude signal. And in fact, today we are able now to correct from that effect. And you clearly see that when we correct for it, the signal completely disappears in the periodogram. So how we correct for them, now I will explain to you. So the main idea is not to correct in the radial velocity time domain, but it's really to correct at the flux level. So let's assume that I have a spectrum and I have a flux anomalies on the right stellar line, for instance. If I want to correct for it with a single spectrum, it's really hard because I have only one single observation. But what I can do is simply take another observation of the star, and then I can even overplot all the observations that I have for my star. And when I do so, I can make a really simple algorithm like a sigma clipping or so on to flag the flux anomalies and remove them. Now, what is implicit if I want to do that is that I need first to normalize all the spectra by their continuum on the full wavelength range. And so to do that, we use the code that I developed at the beginning of my PhD, which is called Racine. So the basic idea of Racine is really to normalize the spectra in a really precise way. And in fact, we demonstrate that thanks to Racine, we were able to have a precision better than 0.05% in flux units. As soon as you normalize all your spectra by their continuum, you can now plot the spectra in 2D. So you have the wavelengths on the x-axis and the time on the y-axis, and the flux level is just the color. So you have this huge matrix, which is a spectral time series matrix. And if I just subtract the mean of this matrix, you clearly see that the flux anomalies that I mentioned before are not random on that space. And the fact that they are not random, it means that you can correct for them more easily. And so it led me to develop this post-processing method that we just published this year called Yarara, where the basic idea is really that you have this huge matrix of spectrum and you try to correct for it with dedicated recipes. And here you see, for instance, an example of the reduction of the systematics with Yarara. So the only thing that you need, it's no more complex than the multilinear regression, actually. It's a basis of vector to fit, the wavelength location where you want to do the fit, and the rest frame to do the fit. And here you see, for instance, a correction of the pattern of interference on HARPS. You also see the correction of the tellurics here and here. And finally, the correction of stellar activity at this stage. I'm just giving you here an example of the amplitude of the signal that we are able to correct. So here you really have the radial velocity effect of each contamination, which is corrected on HARPS. And each subplot is the contamination that is corrected. And you can see that for almost all of them, the peak-to-peak amplitude is above 10 centimeters per second, which is, I recall, the amplitude of a Hertz-like planet around a sun-like star. Here is just a focus on the telluric correction of Yarara. So you see the basic, what are telluric? So it is those absorption lines that are in the Hertz atmosphere, and they are moving on your spectrum and they are changing on depth from night to night in a stochastic way. And if you look now on the time series, they look like these dark purple lines that are drifting. So when they cross the stellar lines, you really have strong systematic in radial velocity on these individual lines. You can see here the RMS, it's around 50 meters per second. And after the correction by Yarara, we were able to go down to 12 meters per second, for instance. Here it's another illustration of the telluric correction, but in 1D. So clearly you can see that he performed a quite good job. And here it's another way to represent it. So what is represented here, it's a polar periodogram. So each dot on this image, it's a line-by-line radial velocity time series. And what we do is that we simply look what is the power at 1 year for this line. And so the power is represented on the polar axis, and the angular variable is simply the phase of the fitted sinus. And so any dot on this image which is above the red circle is a line which was strongly affected by a 1 year systematics. And you can clearly see the improvement before Yarara and after Yarara processing on the systematics of HARPS, for instance. Here it's an example of why you should care about 1 year systematics? In fact, there is, for instance, this star for which there was a planetary candidate published in Feng et al. 2017 at 600 days. And what we discover is that if we apply Yarara, you can see what is corrected at the bottom. It's really 1 year and 1 year over 2 power, which is corrected. The signal that completely disappears is the planetary candidate. Whereas if you look the power at 1 year and 1 year over 2, it don't decrease so much. And so what is happening is simply that you have some crosstalk between a longer signal and 1 year systematic that are producing a peak elsewhere in your periodogram. I will just finish my presentation by give you a few examples of the application of Yarara on several stars. So on the top, you have the classical periodogram from the DRS, from the radial-velocity of the data reduction software. At the middle, it's the Yarara V1 pipeline that has been published this year. And at the bottom, it's the Yarara V2 that I am preparing now. And what you can see is that, for instance, for T-star, we really strongly suppress the 1 year in 1 year over 2 period, whereas the Keplerian signal are boosted by the green arrow. Here it's another example, so just the star that I showed you before, just to show you that the power at 1 year in 1 year over 2 is now really completely removed in the Yarara V2. And you can see that the periodogram that you have on the top and on the bottom are completely different. So clearly you will get different planetary system at the end when you will perform your fits. And I will simply finish with the sun. So here is the application of Yarara on the Harp North solar observation. And the sun is a really nice star because, in fact, we can. It's the only star for which you can be sure that there is no planet. So because we know the planet of the solar system, we can remove them from the radial-velocity, and so you can really see how much you can improve your radial-velocity dataset. And so you know the Harp's North radial-velocity precision is around 65 centimeters per second. If you take now the raw radial-velocity, we are at 1.3 meters per second. When we applied Yarara V1, we were able to go down to 105. And after applying Yarara V2, actually, we were able to go down to 76 centimeters per second. So we are not yet reaching the floor of the instrumental precision because we still see some systematic at long period in particular that are really hard to deal with, but we are really close to that level. And I will simplify. Yes.
Perfect. You have 1 minute left.
Okay. And I will simply finish with that example. So in fact, it's a data set with a star strongly affected by stellar activity. So you see the peak at the rotational period. And so what we perform is that we inject the planetary signal at the flux level inside the spectra. And then I simply apply the Yarara V2 to see if the pipeline was able to recover the planet. And in fact, I just show you the result here. So you clearly see that after Yarara processing, the planetary signal that we injected was the highest one. And I will finish here if you have any question.
Brilliant. Thank you very much. Right on time. We already have a few questions in the plot. First of all, thank you very much for this nice talk from all of us. A question by Melissa Hobson. Do you need to know a priori which effects, for example, stitching or ghost lines, are present in your data before you run the pipeline?
So I would say yes, simply because it's better. If you know what you are correcting for, it's always better than just correcting blindly if you don't know what you are correcting. So, but it's not necessarily. For instance, this is the main difference between Yarara V1 and V2. Yarara V1, we understand what we are correcting for. It's at the flux level. In Yarara V2, we don't understand what we are correcting. We know that it's non-Doppelerian and it's in the time domain. So I would say there is the two approaches that are possible.
Ah, perfect. We have a question by Redian Ahmed, and he's asking, is all of this done in Python?
Yes, yes, everything is in Python.
So all the packages are installable as well, pre-installable, etc.?
No, so the code is not published actually. There is only the Racine code which is published, but the Yarara pipeline is not published. Only the method is described actually.
Ah, okay. Are you planning to publish it?
So I think that we don't plan to publish the code, but perhaps we plan to publish the output of the code. So namely the spectrum corrected from the systematics. Yes.
Nice. So it's something that went like hand in hand with a question that I had. Do you think like eventually this would be possible to include this in one of the codes that Jason Eastman, for example, was highlighting, like ExoFast or Asteroseismology, Juliet or Exoplanet or anything like that, where you do actual like light curve fitting at the same time as like SED modeling at the same time as, instead of fitting, you know, pre-whitened RV data, you actually use your code? Or is it computationally expensive?
Yeah, I think it's quite, it's quite expensive. For instance, for the moment, to reduce a star with the code, it's something already like, yes, 1 day if you have 300 of observations. So if you try to combine that with another code, I think it will be, yes, really expensive. Indeed.
Right. We have another question by David Ziardi. How extendable is Yarara to the infrared, where the tellurics are not as well known as the resolution is poorer?
So I don't know if I have a slide about it, perhaps no. So the only problem that you have is that for Yarara, it's really hard if you are in a regime where there is systematic at any observation. So because the tellurics are drifting, but if you have so much telluric that you always have a telluric covering a wavelength position, it's really hard. So you have to combine that with a more model-driven method, like, I don't know, for instance, molec fit or that kind of code. Theoretically, it's not impossible. But you have to combine it with the model-driven method.
Brilliant. And very last question by Thomas Wilson. Could you build up a catalog of effects for each PRV instrument to use as priors on individual data sets?
Yes, I think actually this is what we try to do with that analysis in the paper, where we clearly demonstrate what was the effect of all the systematic on harps. But now what is important to say is that those systematic usually change from star to star. Sometimes you are really unlikely and they will combine and boost, and sometimes they will just destroy each other. So it will really change from star to star.
Great. And with this, Michael, I'll thank you on behalf of everybody very much again. And thanks also to all of our speakers, panelists, and to Megan for moderating the panel discussion today. And I hand over to Avi Sporer, who will talk us through how the next poster session will go. And then I'll see everybody again in the afternoon for our continued data analysis session. Avi, stage is yours.
Thank you, Max. Quick announcement first about the poster competition. There are a lot of posters in the competition, over 100. And we don't have enough judges to do a thorough, adequate, quantitative evaluation of each poster. So what we decided to do is have only a certain number, probably a single-digit number of posters that we will have honorable mention. And we will announce those honorable mentions at the end of the early session tomorrow on Friday. And next, I want to quickly go through GatherTown for those who are not familiar with it. So for those who are familiar with GatherTown, you can close the Zoom webinar and jump on GatherTown. So for those who are not familiar with GatherTown, just want to show you how it looks. Once you click on the link, which I just sent on the general Slack channel, and is also available in the detailed schedule PDF, you would see this screen. It will probably take you through some introduction to Gather. It will show you a few things, but eventually you will get to this screen. And you can click on Edit Character, where you can enter your name. Please enter your full name so people know who you are. You can play with the avatar itself, make you look in certain ways. You can do crazy, just weird things, funny things, whatever you like. Also, the color of the clothing and the hair can be different. So again, feel free to use your imagination. Then you click Next. You can open your microphone and camera. I'm not opening them now because I am using them on Zoom, but you're encouraged to open them as you go into GatherTown and join the gathering, and you will reach the main room. I am right here. So many things you can see here. There are avatars of other people. You can see their names. They're walking around. People who are close to me. People who are close to me, I can see their camera turning on and they can hear me and I can hear them, for example. Yeah. So I will walk away a bit and be rude to those other people. And you can see there is entrance to poster halls. So there are, so we can go to one of those poster halls and you can see many posters. Note that sometimes you walk into this poster hall and it can take up to 5 seconds for the posters to appear. It will look empty, but give it a second. Then you can walk up to one of the posters completely randomly, click on the X, and you can see the poster. This is a completely random poster, but it does look interesting. They try to look at light curves through the eyes of the machine, literally like using graphic processing to determine if it's a transit or an eclipse. And you can close the poster, click on this X, and you can then go to another poster or another place. So let's go back to the main hall. Besides posters, there are many other things here, and you can feel free to explore it and walk around. We have the TOI help desk here, where there are people from the TOI team, so you can feel free to walk up and ask any and all question you have about TOIs. There are actually some, dare I say, fun stuff in GatherTown. You walk to this beach area, you can start hearing the waves. I'm not sure if that audio transfers from Gather to Zoom, but when you are there, you can start hearing the waves. There is actually a beach here, and you might wonder if you can drown, so you cannot really go into the water. And a few things here. There is a virtual piano here that you can play through the keyboard, and there is some video game like Tetris here. You can also play and compete with other people. And one other thing, there is a roof area. You can just walk through this door and then you appear in another world. This is like a roof area. There is like you can hear I hope you can hear, there is like a small campfire here you can warm up to. And then you go back here where you see the exit sign and you go back to the main room. One thing I didn't say yet, how do you know where a certain poster is located? So you see these boards, there are 3 of them around this room. You walk up to them, you click on the X, then you do need to wait a few seconds. It is loading a spreadsheet. This is the spreadsheet. So the poster location is encoded in the poster ID in this leftmost column. The integer part is the whole number from 1 to 9. You can see there are up to 9, goes all the way. There are almost 200 posters here. So for example, 905 is whole number 9. You look for it in the main room. You see the entrance to poster hall number 9, and it is poster number 5 in that hall. And another example, just randomly, 403 is hall number 4, poster number 3 in that hall. And you can just close this, click on the X, and you are back here, and you can see there are up to 9 poster halls, and that's it. So it's a lot of fun. Another interesting feature, you can see all the people inside GatherTown listed here on the left. You can see there are 125 people right now inside the GatherTown space. if you see someone you know on this list and you want to walk up to them, you don't see them on the screen, but you see them on the list. So you want to find them. So a very cool feature, maybe a bit creepy. You can, here is Hugh Osborne. I know him, he's from MIT, so that's okay. I click on his name, and then you can send him a message, like with a chat. You can follow him or locate him on the map. So I just located him on the map, so we can walk up to him. He's in poster hole number 3, and here he is looking at a poster. So that's how you can find people. They don't know that you're just walking up to them. It doesn't appear in their, there's no feedback for them. Okay, this is it. I do recognize this is the newest online feature or online tool we are using, so that's why I'm trying to show it. Many people are not familiar with it, as opposed to Zoom and Slack, which we have been using for years now. It does seem a bit weird. It does seem a bit new. It did seem weird to me and very new to me up until very few months ago. And then I quickly realized this is awesome. This is great. This might be the next step in the evolution of online meetings. I encourage you all to go on GatherTown, look at the posters, find some friends or colleagues you haven't seen for a long while and walk up to them, say hello, ask how they are doing. Or you can see some people like here, I see James and Emily and Tara talking together. I can just walk up to them, say hello, and see what they're talking about exactly as I would in a real conference. That's the idea here. So I will stop now. And you are all welcome to go on GatherTown. If you want to leave GatherTown, you can just click on the back button and you go to, you will see a different screen when you step out, but that's all, that doesn't really matter. So we have like now almost an hour left for the poster session. And after that, we are back for the second session of the day at 3:30 Eastern, 7:30 p.m. UT, 9:30 p.m. Central European time. We will continue 2 talks about data analysis and then go to sprinter sessions. So see you in the next session.